In order to use big data effectively, organizations need to use it in conjunction with operational data sources which exist within the business. In this video, you will learn about the various important data sources and services and how these are used with big data solutions to achieve the desired results. The focus of this video is to take you through the different database systems relevant to big data and introduce you to data warehouses. The first database management systems that we will discuss are Relational Database Management Systems, or RDBMS. In organizations, RDBMSs are the primary storage repository for important operational information. Different RDBMS exists for different areas of business. For example, transactional data might be stored in a vendor's database. Customer information could be stored in another database. Knowing what data is stored and where it is stored are critical building blocks in your big data implementation. The best example of an RDBMS is PostgreSQL. It is the most widely used open-source relational database. It is highly popular because of being time-tested and its compatibility with every variety of operating system, from PCs to mainframes. PostgreSQL supports foreign keys, triggers or events used to automatically start a stored procedure, complex queries, transactional integrity, to name a few. Users can keep adding new capabilities without affecting the current version. The extensions can be in the form of languages, operators, functions, and so on. Now, consider data from multiple RDBMSs being stored in one place and available for access to gather business intelligence. Such a repository would be what is called a data warehouse. According to Gartner, a data warehouse is a storage architecture designed to hold data extracted from transaction systems, operational data stores, and external sources. The warehouse then combines that data in an aggregate summary form suitable for enterprise-wide data analysis and reporting for predefined business needs. In simple terms, a data warehouse is just a permanent storage space for data needed for analysis, reporting, and other BI functions. The reports generated and the results of the analysis help in decision-making across the organization. Some of the industry-acknowledged benefits of data warehousing are that they provide a unified view of the enterprise, serve as a single source of trustworthy data, serve as a unified metadata repository, support ad hoc reporting and business intelligence, support data mining and analytical applications. So what do data warehouses typically do? They store data for a long period of time, consolidate it when it comes in from different sources, including metadata, and save it in formats which aid high-speed information retrieval. Data warehouses have the potential of being the key providers of structured data that business intelligence tools and applications can crunch at the press of a button and come up with amazing business intelligence. So you have answers to questions like, what happened? What is happening now? Why did it happen? And even, what is likely to happen next? Data warehouses reside on dedicated computers reserved for this function and run on database management systems. Now that we understand what data warehousing is, let's look at Online Analytical Processing, or OLAP, a term which is sometimes used interchangeably with data warehousing. The function that OLAP performs is the processing of data by slicing, dicing, filtering, drilling up, and drilling down data to derive insights that would be useful to business users. OLAP's multidimensional data model, commonly known as CUBE, and data aggregation techniques organize and summarize large amounts of data so that it can be evaluated quickly using online analysis and graphical tools. This technology enables the effective use of data warehouses for online analysis, providing quick responses to complex queries. Thus, data warehouses have become the source for data mining, analytics, and dashboards. The components of a data warehouse are 1. ETL, toolset that helps acquire a variety of data from multiple sources. 2. The warehouse. This stores data, or facts, and multiple perspectives from which these facts can be analyzed, called dimensions. 3. Metadata, attributes that could be associated with fact, including source, format, update frequency, etc. 4. Cube, OLAP data structure that is extracted from data warehouse for specific subject analysis like sales, attrition, etc. 5. Reports and dashboards, the visualizations that provide business insights. To ensure that warehousing is effective, the data in the warehouse should be stored in a way that has consistent definitions and the most up-to-date values. It should be subject-oriented and organized so that related events are linked together. The information should be non-volatile so that it cannot be inadvertently changed and should include all the applicable operational sources. So what are the benefits that a business derives from using data warehouse-centric big data systems? The first benefit any business earns on implementation of data warehousing is strategic alignment and enhanced corporate performance visibility. The second benefit is increased team collaboration. The third benefit is an environment that builds a culture that promotes fact-based decision-making. The fourth involves non-violation of compliances. Data warehousing-centric systems provide a platform to develop applications to track enterprise-wide regulatory compliance. The final and fifth benefit is improved business processes. So how are big data analytics and data warehouses connected? The advent of big data is challenging the traditional role of data warehouse. Big data analytics involves analyzing a mix of structured, semi-structured, and unstructured data in order to provide actionable business intelligence. The traditional data warehouse supports structured data. This concept of data warehouse is now changing. New kinds are coming up to suit new ideas and cases. The new kinds are optimized and architected to include other types of databases so that they remain relevant for big data. Apart from RDBMS, there are also other types of databases that contribute to big data solutions. Let us look at some of these. Non-relational databases, as opposed to RDBMS, are a database which do not abide by the table key, that is to say, schema model endemic to RDBMS. The key challenge of the big data world is the inability to define schema before storing any type of data. Therefore, such database systems require different techniques to tackle and solve big data-related problems. While they offer some answers to big data challenges, they do not guarantee success. Some of the characteristics of non-relational databases are scalability, the capability to write data across multiple data stores simultaneously and seamlessly, and the ability to expand and contract in response to data flows and without being visible to the end users. The data and query model that use specialty frameworks to store data with a requisite set of specialty query APIs to access the data intelligently. Persistence design, which guarantees that the data stored in a database will not and cannot be changed without permissions, and that it will be available for as long as it is important to the business. And last but not least, interface diversity, offering a wide variety of connection mechanisms for programmers and database managers, and eventual consistency, which is responsible for conflict resolution when data is in motion between nodes in a distributed implementation. The dataset is maintained by the software, and the access model relies on basic availability. The most commonly used non-relational database is the NoSQL or Not Only SQL. Some of the most popular styles and the open-source implementations of non-relational databases are Key Value Database, Document Database, Columnar Database, Graph Database, Spatial Database. We will discuss each of these in detail. Let's take up the Key Value Pair, KVP model first. The Key Value Pair, KVP model, is a set of two linked data items. These are used by the simplest kind of NoSQL databases and are extremely flexible and scalable. Hence, with the increased number of users, the KVP count associated with each automatically increases, creating an exponential database. Therefore, it is important to choose the correct KVP database to control the important aspects of the big data management. REAC is a widely used key-value database. The next type of non-relational database is document database. You find two kinds of document databases. One is often described as a repository for full document-style content, for example, Word files and complete web pages. The other is a database for storing document components for permanent storage as a static entity or for dynamic assembly of the parts of a document. The structure of the documents and their parts is provided by JavaScript Object Notation, JSON, and/or Binary JSON, BSON. Document databases are most useful when you have to produce many reports, and they need to be dynamically assembled from elements that change frequently. Two of the most popular implementations of document databases are MongoDB and CouchDB. Columnar databases store information in the form of columns instead of rows. When you have volume and variety of data, you might want to use a columnar database. It is very adaptable. You simply continue to add columns. HBase is the most popular example of columnar database. It relies mainly on Hadoop file system and MapReduce for its operation. Graph database is another popular form of non-relational database that uses graph structures to store and use data. These kinds of databases are useful when highly interconnected data is involved. Neo4j is an example of a widely used graph database. It is an open-sourced project. Spatial database is a database of data or information about elements present across various geographical areas and locations. PostGIS OpenGeoSuite is an offering from the Spatial Database family. This software enables information to be organized, visualized, and analyzed. The Big Data Challenge doesn't end with different types of databases and data warehousing. There are many situations where data is being captured continuously at very frequent intervals, typically from electronic sensors and devices. This is called streaming data. Such data requires complex event processing algorithms. New tools and technologies are emerging every day to process such continuous streams of data. Now that you know about the relevance of database systems to big data and data warehouses in big data, let's see how much you can recall. If you selected MongoDB, REAC, and Neo4j, you are right. All of these are examples of non-relational databases. Let's do a quick recap of what you've learned in this session. Big data is a term for large or complex data sets for which traditional data processing applications become ineffectual. Big data is used to derive specific and other useful business information. Relational Database Management Systems, or RDBMSs, is the primary storage repository for important operational information. A data warehouse is a storage architecture designed to hold data extracted from transaction systems, operational data stores, and external sources. OLAP involves the basic framework for data analyzing. Data warehouses use metadata to track the data source and its attributes. A non-relational database does not abide by the table key, that is to say, schema model, upon which RDBMS is based. The different types of non-relational databases are key-value database, document database, columnar database, graph database, and spatial database.